Hi everyone, welcome to this exciting World Space Week talk show series where we are going to explore the role of geology in space science and India's role in space race. I am your host Bharti Sharma, geologist and founder of AADYA Planetary and Geoscience Research, a trailblazer in the field of collaborative research and geotourism. It is a startup that is actively involved in geoconsultancy, skill development, and geology field training program for students. And today I am honored to share my screen with Dr. Chandra Mohan Nautiyal Sir, a distinguished scientist whose contributions to the field of isotopic measurements and its application in planetary science, geology, archaeology, and environmental science and science communication have left an indelible mark on the scientific community. His expertise has been sought after in countless workshops, webinars, and science film festivals, where he has imparted his valuable insights to aspiring scientists and filmmakers alike. Thank you so much, sir, for giving me this honor today.
Welcome to this forum. Thank you.
To begin our conversation, sir, I would like to ask you what motivated you to study the isotopic measurements and to specialize in this field?
Actually, it wasn't isotopic measurements per se, which enticed me to this field of planetary geology or planetary science. Actually, when I joined Physical Research Laboratory way back in 1977, after we completed our coursework, we had to select our group. So we were all exploring and talking to different faculty members. And then it appeared that the head of one group, geocosmophysics, Professor Devendra Lal, was a very distinguished planetary and geoscientist, basically a physicist, but he was working in the moon samples and meteorites and such stuff. So I decided to meet him. There was another person who was also interested in working with him, that group. So we both met him, and then he sort of interacted with us. But I think it was a form of interview. So he asked us about meteorites. Have you seen a meteorite? Have you heard about a meteorite and all? We didn't know. We were absolutely in dark about what meteorite is, except what little we had understood during our coursework. And then he started explaining to us what meteorite was. And then it turned out that if you want to study meteorites, one of the very important things to analyze is the isotopic ratio present in those meteoritic samples. As it turned out, he picked me, and I was working on this project there for the next many years. Initially, I also did a little bit of work in tracks, cosmic ray tracks. But then I moved over to noble gas mass spectrometry, and my main interest became that argon, neon, helium, and such noble gas isotopes, because they offer clue to the processes. This is something very interesting. These are noble gases, which means they don't chemically react. So if we find some noble gas in some sample, it's obvious it has come from some extraneous source or from source within that, but not a chemical reaction. If you look for oxygen isotopes or nitrogen isotopes, they could be coming from the nitrates, from the oxides, from the silicates, or from such stuff. But noble gas means the presence of noble gases would be very small. So as a tracer, noble gases are very important. And these ratios could not have been changed because of any chemical reactions, because they are chemically inactive. They don't react. So we particularly focused on neon isotopes. And when we studied the moon samples, which had been brought by various missions by NASA and then Soviet Rus, which means Luna mission and Apollo mission, we found that in some of the samples, which were aluminium rich, present, and we analyzed the feldspar component of the lunar soils. And we found that the ratio of neon, that is neon 20 by neon 22, and neon 21 by 22, were a bit different from what we were observing in samples like olivines, which were magnesium rich, or in pyroxene, which were magnesium rich. So this gave us a clue what could be happening on the surface of moon. And then it turned out, by studying the aluminium-rich feldspar samples from moon soil, that these samples were exposed to the cosmic rays coming from the sun. Also, the outer skin of these small 100 micron, 60 micron, that kind of grains, these grains were very rich in solar wind gases in their outer skin because they were low energy particles coming as part of solar wind. They could not penetrate deep inside the grain. They would be confined to the outer 1,000 angstroms or so. So this is how we got interested in isotopes. So as I said, it was not isotopic ratios per se which interested me. What enticed me was the moon samples and the meteorites because of tremendous secrets of the solar system formation, early solar system formation they hold within them. Some of these meteorites are from the olden times when solar system was forming. And people believe that these are those bodies which could not become planets. So today we find these asteroids revolving around the sun between the orbits of Mars and Jupiter. And most of the meteorites that we receive on Earth are coming from this asteroidal belt. Some of them come from Moon, some of them have come from Mars, like Shergottites and Nakhalites and Kazinites. They come from the Mars. There are some samples which came from Moon. And one of them was, which was recovered from Allen Hills in 1984, 84001. And that meteorite, people suspected contained traces of a bacteria. Of course, later, the claim was dismissed. And that was also, again, interestingly, based on the isotopic ratio of carbon present in there. That is carbon 13 by carbon 12. So this is what interested me to isotopic ratios.
This is indeed interesting. Even I am getting interested in isotopic measurements because it is touching all the bases for the chemical evolution of rocks and life on Earth and on other planets as well. So you have dealt with lunar soil, lake sediments, coast sediments, pollen, glacier and meteorite samples, as you said. You have worked with a diverse variety of samples. Given your wide expertise with variety of sample types, could you share an example of particularly interesting project where you have felt that isotope measurements have contributed to a crucial finding in that context?
Yeah, what I'm going to say is about so-called gas-rich meteorites. Normally, as I said, the particles coming from the sun don't have that much high energy as the cosmic ray particles from the galaxy, what we call galactic cosmic rays. These cosmic rays coming from the sun, or we call them solar energetic particles, a solar corpuscular radiation, they're coming from the sun. So those which are coming as solar wind have very low energy. They are of the order of kilo electron volts and so. But those which are coming from the sun, from the inside of the sun, they have million electron volts or up to 100 or even a little more million electron volts. They are highly energetic. So imagine a grain which is about 1 millimeter in size. If it's exposed on the moon surface, for example, the particles are coming from the top. They will penetrate up to 1,000 angstroms or so if they are from the solar wind. They will penetrate maybe to 0.1 millimeter or 0.2 millimeter if they are coming as solar cosmic rays or solar energetic protons. Now, if we take a sample from inside of a meteorite, which could be several centimeters or even meters in size, we don't expect to see such evidence of low energy particles inside them because the low energy particles could not have penetrated 5 centimeters, 10 centimeters, or 1 meter of that meteorite size, right? But we did came across once, which was very interesting. We put that sample in the mass spectrometer, and all of a sudden we observed that the signal went shot up like anything. And we both, myself and my senior colleague, Dr. Venkatesan, we were nervous. I mean, nothing was within the scale. It just shot off. Now, at that time, a presence of mind occurred, and I realized that if we change the input resistance of our sense amplifier from 10 to the power 13, if we change it to 10 to the power 10 or 10 to the power 11 ohms, the signal will go down by a factor of 1,000 or so. So we immediately did that, and then we were able to make the measurements. And then it turned out that this meteorite, which had been recovered from Antarctica, was actually a gaseous meteorite. Not that we were the first people to study gaseous meteorites, but this was for the first time that unprepared we had come across a sample which was actually a gaseous meteorite, which means inside a bigger body there was a small portion which had sometime during the history of the meteorite been exposed on the surface of a planetary body. And later, because of impact on the surface of that parent body, it recompacted. And what was on the surface of the planetary body became inside of the planetary body. So now, this part was hidden inside several centimeters or maybe several meters or tens of centimeters of a body, and now this is inside. So originally, it was on the surface. So this is what gas-rich meteorites are, and many of them are believed to have formed during the very, very early stage of the solar system formation, which means these have records of the early solar system formation stages. So these are our records. We cannot go back in the past otherwise, but these give us the radiation records of that period when the solar system was in its early stages of evolution.
Wow, that was really insightful, sir. I am pretty sure for so many students, this is going to be an inspiring story, and to study the chemical origin of solar system and the isotopic measurements. Sir, as you have worked on multiple meteorite samples and you have worked in the space science domain, my next question for you is, what are your thoughts on India's recent advancement in space exploration, particularly in missions like Chandrayan 3 and Aditya, and how do you perceive their contribution to scientific discoveries and insights from these missions?
As we all know, America and USSR, then USSR, were way ahead of us in space science. They started working on them in 40s and especially in 50s. Yuri Gagarin, even a space cosmonaut was sent by Russia. They sent a Sputnik. Then US all of a sudden came from nowhere, and in 1969 they pipped the Russians on the post, and they landed on the moon. And a long race which had been going on for many years between the USSR and America ultimately turned in favor of United States, and they were able to land their Apollo 11 on moon. And from then started a long series, 11, 12, 14, 15, 16, 17, many American missions and also many Russian missions of Luna, Luna 20 or Luna 16 or Luna 24 and others. They brought back samples from the moon. In fact, Apollo missions, I think, brought something like close to 400 kilograms of lunar material rocks.
Yes, sir.
And we should not call them actually soil, we should call that regolith. And there is a reason for that, I'll just explain. About 370, 375 kilograms of solid material was brought from the moon to Earth, and part of it was distributed all across the globe. And India happened to be one of those countries. Professor Nal at that time was a principal investigator for this project with the NASA institution, and I happened to be a scientific collaborator in that. So when sometimes people ask me, did you touch the moon samples? Honestly, not. We only held them with tweezers. We were not given you like a 1 meter chunk of lunar rock. Many of the rocks were very huge. For example, you may have seen some photographs where the cosmonaut Schmitz is standing in front of a rock, which is some 5 to 10 meters long.
Yes, sir.
So that is not the kind of rocks that were brought here. Smaller rocks like 6106, 79215, or 64435. These rocks were brought by NASA, and the slices were cut out of them, and they were distributed across the globe. Similarly, the lunar regolith. We call it regolith for a very, very vital reason. When we say soil, we are talking of the soil on Earth, which contains biological component. The plant debris, the pollen grains, or maybe even micro fossils, which paleontologists study. All this stuff is a part of soil. But lunar regolith or dhool, we should not call it mitti, perhaps we should call it dhool. That is a result of a different process than Earth. In case of Earth, there is water cycle. Water is carrying the sediments all the way from the top of the mountains. then also there is some erosion. But in case of moon, there are no winds. So there is no erosion because of wind. But still we see regolith there or find dust there. Where does it come from? It comes because the moon surface does not have atmosphere, nor does it have a magnetic field. Therefore, the micrometeorites and meteorites which are bombarding constantly its surface, they bombard these lunar rocks, and that results in formation of this dust or these particles, and they, they go all over. And then a huge impact occurs, and whatever regolith is there, this is lifted off. But gravity is anyway 1/6 of that on Earth, so it spreads all over, and we see soil there. There are some parts where you don't see much soil, that is the lava-rich region. What you see there as black region is mare or the lava-rich region. But then there are highlands which are white, and these are feldspar-rich soils by and large. You must be knowing that there is no new element found on the surface of moon in any rock or any regolith sample. But 6 new minerals have been found there. The latest one being by the Chang, the Chinese spaceship which landed there. Changisite, that's the name which has been given to that. So otherwise, it's not very much different. One major difference is that it's dominated by feldspar compared to olivine or pyroxene. And therefore, the color of the soil there is brighter than that on the Earth. Second difference is that in case of moon, the surface regolith is being constantly reworked because of micrometeoritic bombardment. What is on the top today may not always remain on top. This will go down from somewhere else because of an impact. This regolith may jump up and then settle down on the older regolith. So this is being constantly reworked, and also this is being powdered.
So this is impromptu question, but I would like to know what are your thoughts on is lunar or moon is an active celestial body or not? Like as you said, the process is still going on with the lunar regolith mechanism. So is it a still active celestial body or not?
Moon, as is so far believed. Of course, let me also add something to my previous statement. Earlier, 40 or 50 years ago, we had to depend on USSR or USA for studying moon samples. Yes. Now, with our own lunar mission, having reached the soft landing stage, Gaganyaan in plan, which will go up to 400 kilometers in altitude. Later, we are planning by 35 and 40, we are manned missions to moon, and perhaps we'll bring back the moon samples. So I think these missions are very important in the sense that we don't have to depend on other countries for getting lunar samples. Our own missions will go there and bring back samples from there. So that's why this recent Chandrayan 3 mission becomes very important for us. Now, coming to this part of your question, please repeat the question, this part.
I would like to know your thoughts if lunar celestial body or moon is still an active celestial body. Like, okay. Are the processes still going on, or it will be considered as dead when it comes to processes?
Yeah. Okay. First, to the origin of moon, many people believe that during the early history of Earth, a Mars-sized body came and hit Earth, and the surface material, which is a crystal material, that was excavated out, that formed a ball-like thing, which was revolving around the Earth, and it compacted into forming moon. So this is the impact origin of moon, which is generally believed. Some people think that there could be 2 such bodies formed, and maybe we lost one of them, and maybe the 2 coalesced together to form a new body. This is still not 100% clear. Now, whether this is, so in that sense, this was a part of Earth initially, and it did not independently form in space. So in that sense, it was not a celestial body other than Earth. Yes. Second part is why we believe so. If you look at the overall density of moon, it comes to about 3.3 grams per cubic centimeter. If you look at Earth, the average density is approximately 5.5 grams per cubic centimeters. But if we look at the crustal part of Earth, this is less than 3.5 grams per cubic centimeters. And the average density is 5.5 grams, which clearly establishes somewhere in the Earth there is material which is far more dense than the surface material. And that is the nucleus or the central or the core of Earth, where you have heavy elements like iron group elements, chromium, even uranium, thorium, and such heavy elements. So at the top, the density is 3.5 grams per cubic centimeter. In the center, it may be 8 or 9, or maybe because it's compacted, it can be even higher. And therefore, the average density of Earth is somewhere between the two, these two extremes, which is 5.5 grams per cubic centimeter. But now you see the similarity of density between crust of Earth and the overall density of Moon, which are almost equal, which gives credence to the opinion that Moon formed out of the crustal material of Earth. Then some isotopic similarities have also been observed in oxygen between Moon and Earth. So people believe so far that this formed out of Earth. But now, whether this is geologically active or not, generally people believe, so far they have believed that this is a geologically dead planet. But the recent Chandrayan has produced evidence of sulfur on the surface of Moon, which is something by itself, this shouldn't surprise people because sulfur is a common element on Earth also. But if you see it on the surface, this is a bit surprising because chances are that it came from the interior during the volcanic activity. Right? But Moon, we say, is geologically dead. There is no crustal movement. Again, people are still talking of moonquakes. There is an instrument about Chandrayan-3, which is there to, we cannot call it Bhukam because this is not Bhu. So let's call it Chandrakam or moonquakes. So there is seismometer equipment aboard Vikram, which is making measurements in case there are any moonquakes. But moonquakes cannot occur unless there is some kind of either crustal plates movement or some kind of this thing. Of course, there is another possibility how moonquakes can occur because Moon doesn't have atmosphere. So any solid body like a meteorite, if it's falling on the surface of Moon, it will come and impact its surface, and that can cause small earthquake, that can cause seismic activity. It will not be from the interior, it will be confined to the surface part of the Moon, but that can be there. But otherwise, any seismic activity inside so far had been ruled out. But if there are moonquakes, then people have to look at it again. And the presence of sulfur again gives rise to the speculation, is something still happening inside Moon? So we don't really know too much about Moon yet. Much of it is speculation. And a large amount of stories have been built up based on the not geochemical, I think moon chemical or whatever you call it, the elemental and isotopic measurements on the materials of Moon. So I think that stories have yet to be built up completely.
Thank you so much, sir, for the insightful answer. Now I'll jump from the core science branch to science communication. So as a country which is as diverse and populous as India, science communication plays a crucial role in bridging the gap between scientific advancements and the public. Could you share your perspective on the challenges and opportunities of science communication in India and how it can be further enhanced and inspire and educate a wider audience?
I think a very important question. Asimov has said that a society that does not understand science cannot appreciate it.
Yes.
It was a long quote, I am just giving a summary. If people don't understand science, they're either afraid of it or they worship it.
Yes, sir.
Neither is a situation, a very happy situation for the society. Therefore, it's very important to make people understand and appreciate science, because otherwise they think that scientists are people who make weapons of mass destruction particularly, and so they can even hate science. And I can assure you there are people in some parts of the world who think that the scientists are people who are after money and they are making nuclear bombs and all. Even if you talk to them about nuclear energy, they always take it as nuclear bomb. So I think it's very important that we make people appreciate science, and this can be done only by communicating science.
Yes, sir.
Today's society, everybody in the society, I am not talking of Jarwa tribe living somewhere in Andaman Nicobar, who are cut off from the modern gadgets or modern thing, but otherwise almost everyone on this earth is connected to each other through science and technology. In everyday life, we cannot imagine a normalcy unless we have science and technology coming to our help, whether it be transport, whether it be communication, whether it be food. And the modern generation is perhaps growing up believing that agriculture happens inside the departmental stores. But even in agriculture sciences, it's science which has made us self-dependent. So I think there is no more debate possible on this question whether science and technology are important to us or not. They are. But we should make people appreciate that so that science and technology gets more support. Dr. Kalam used to say that we should spend something like 2% of our GDP on science and technology. There are countries which are spending close to 4%, and they are much smaller countries than us. And we used to spend 0.8 or 0.7 or 0.6% of our GDP, which is hardly adequate in this age. So if we want support of people for science and technology, we must help people understand and appreciate the role of science and technology in life of people.
Yes.
So science communication is very important. This is one reason. Second reason is in our everyday life, some minimum knowledge of science is important. When I say science, I am including technology.
Yes.
Some minimum knowledge of science is essential for everybody. Everyone uses gadgets in the kitchen. If they don't follow the basics, they will be wasting more electricity. They will always have a fear of shock. If the housewives are, so-called housewives, are not told about the basic principle, how to save themselves from electrical shock, I think this could be lethal. If we don't tell them why we should, how we should use the gas equipments like gas stove and such things, this is a danger to their life. If you don't tell them how to drive safely, if you don't tell them why vaccines are important. And I'll tell you one interesting aside. Nature published a result of a report by some people, some survey, and they said that during the COVID period, 50% more journalists got interested in science. When it comes to life, when it comes to health, everybody comes to science and technology. And I think in that way, I mean, very many tragic things have happened during the COVID phase. But one good thing has happened that people can go to worship, people can pray, people can respect anybody, people can worship and all. But when it comes to their life, they all turn to science and technology. But for the vaccine development, many more people would have been dead during the COVID phase. So people do appreciate the role of science now after COVID much more than they did before. So we have to communicate science, but there are challenges. One challenge is that the commercial interest of the media. You would see that in many of the channels, including I think some government channels, more time was allotted to science and technology initially. In fact, television in India started with the very noble aim of taking education to the household, the doorstep. The site by Professor Yashpal, that was a step in that direction. But gradually now entertainment, stories about the Nagin taking its revenge and so on, they have dominated over the science. And see, science can at times be drab and dull. So one challenge is to take science to society against these odds of commercial interest of people who want to sell you all the bad stuff. They want to stuff with everything which is toxic. It doesn't help your health. It doesn't make you healthier. But they are selling, we are paying money to buy poisons. Now, in this case, and that is always more attractive, more tasty, more delicious. In this challenge, we have to promote science. So we have to link it to the interest of the people. We have to link it to the future of their children. We have linked it to the interest of their children. We have linked it to their economic interests. So this is a challenge, how to make science more presentable, more interesting, and convince people that this ultimately will be helping them. This is a challenge against the commercial interest. Another challenge is that let us not mix science with things which are not scientific. There is another fashion. For example, I always respect our ancient people who did wonders in the fields of mathematics, in field of architecture, in field of chemistry, in field of metallurgy, in mathematics, in astronomy, and many such fields. But that does not mean that everything had been discovered in the ancient India. There are many things which have now been established, even though they are popular in the world in the name of other people. For example, what is called Pythagoras theorem. Actually, the first statement of Pythagoras theorem was given by Buddhayan as a prameya, and not by Chinese or by Egyptians. Egyptians perhaps were knowing about it, but they never stated it. India did it first. But again, in India, we did not find an evidence of the proof. Instead, we only found this evidence in China. So everything was not done in India. We have enough to be proud of. We have had such a brilliant past. We have to be proud of that. But let us not mix imagination with science. So that is another danger, because some people just are turned off if we try to tell them everything had been done in India. That is another challenge. We have to control that temptation. In addition, we have the challenge of increasing complexity of fields. Earlier, the concepts were somewhat simple, and those simple concepts could be explained to people in many simple manner. But now we have DNA, now we have stem cells, now we have many such things. So explaining them to people is becoming more and more difficult. So this is another challenge. Then increasing fields. We can today see there are many fields in the field of science today, and in this field we see so many things. So how do we find experts or people who can explain it to people in simple manner? So more and people with background in science. And it's not necessary that they all should be from a single discipline. They can be from physics, they can be from geology, from chemistry, from mathematics, or astronomy, or astrosciences, and several other fields. So all these people some of these people who have communication ability. One thing is very clear. Generally, journalists will be doing journalism, and scientists will be doing science. But then there is a meeting ground between the two. Some of the scientists are very good at communication, but very few. Similarly, some of the journalists have had background in science, and therefore they understand science. But then there could be some scientists who want to switch over to science communication, or even while practicing as scientists, they can communicate science. So I think such talents have to be identified. And this is one big challenge for the government and for the government organization to scout for such talents and encourage them to promote science. So I think this is another big challenge before science. There should be organizations. Unfortunately, one organization was closed down, but I am sure that many more and bigger alternatives will be coming up. We should have some established organizations in this country who promote science communication.
Thank you so much, sir, for the answer. I must say that I can't agree more on the thought you said, that a society which don't understand science will not appreciate it. Either it will worship it or it will be, scared of it.
Yeah.
So science communication is important, because whatever scientists or we are doing in the field of science is worthless if people don't understand it, what we are doing, and if it is good for them or not, and how it can be beneficial in their daily life. So to wrap up our discussion, what advice would you give an early career researcher or future scientist who wants to make a career in space science?
I think space science has tremendous potential now. Those who are very young, for example, in 10th standard or so, they should, if they are interested in space science, they should aim at this. And there are programs like INSPIRE program. Now there is one Indian Space Science University, Indian Institute of Space Science in Trivandrum. They should aspire for admission to that. They should score high in their examination. And more importantly, they should understand the subject. So that is a new possibility for the young people who are aspiring to become space scientists. And even if they don't get into that institution, they can get into many. Now there are so many IITs, there are so many NITs, and NICER and such institutions, ICERs and so on. And even if they don't get into some of these hallowed institutions, they still have tremendous scope in space science. For example, you won't find many IITians or ICERs people working in the space science department of the country, which have taken Chandrayan 3 to the moon.
Yes, sir.
So this is not so much where you studied. What is more important is how much and how sincerely you studied and how well you did it that. So if somebody is interested in space science, opportunities are emerging. In coming 10 to 15 years or so, India may be having its own samples from the other planets or satellites. India will be sending many more missions to Moon, to Mars, and Venus is also in offering. So many more space scientists and technologists are needed for that. So if somebody is genuinely interested in that, two things are very important. One is, of course, that working hard and working very intelligently. Second thing is they should specialize in one particular field, but at the same time, they should not shut themselves from many other fields. For example, I did my MSc in physics from what is known as IT Roorkee, but I did not confine myself to physics alone. When I started working in space science at Physical Research Laboratory, and later when I started working in Birbal Sahni Institute of Planetary Sciences, I was heading the radio power dating laboratory there afterwards. Of course, this had little to do with space science, but I was all the time interested in space science. So if you want to work in space science, even if you are studying moon samples, you will have to apply some geology, some geochemistry, some physics, some earth, what you call earth science, geoscience, or planetary science. So planetary science is nothing but a mix of these different aspects which you are doing for Earth. So you have to be multidisciplinary, but yes, you should focus on one particular field and specialize in that, but keep your eyes and ears open for work in other areas also.
Thank you so much, sir. Indeed, it is true that space is for all, be it a physicist, chemist, geologist, artist, communicator. Space is inviting everyone. And I must say that whosoever is studying in 9th standard, 10th standard, space is the thing for their future, like for the career path. So, as we conclude this enlightening conversation, I would like to extend a heartfelt thank you to our esteemed guest, Dr. M Nautiyal Sir, for sharing his insights and expertise. Thank you so much, sir, for coming to our show.
Thank you very much, and all the best wishes for your startup. I hope it does very well.
Thank you so much, sir. It means a lot to me. So, to our audience, stay curious and keep learning. Follow us on social media to stay updated on the latest on planetary geology, Indian space missions, and geoscience. Keep striving for the stars and explore the mysteries of the cosmos. Till next time, namaste. Thank you. Thank you so much, sir.
Thank you.